Let me start recording. And so any questions, comments before we start? Start sharing my screen. Okay. If no questions, then let's start the lecture. So, okay. So last time we started talking about random matrices and basically concentration or non-asymptotic bounds on random matrices. The first thing that we looked at was the norm, the operator norm bounds on the operator norm of a matrix that has independent zero mean sub-Gaussian entries. And so each entry has a sub-Gaussian norm, and we assume that these sub-Gaussian norms are bounded uniformly above by k. Okay, and then you have this bound with high probability that the operator norm is bounded by a constant times k times basically root m plus root n plus a deviation t, which appears in the probability bounds. So the key point was that if you look at a general matrix whose entries are all 1, then let's say the entries are in -1 and 1, then you could come up with matrices whose operator norm is at most, or at most n, and in fact n. So the operator norm would be at most n, but you can also come up with things that are whose operator norms are of the order of n. Whereas this result is saying that if you choose them randomly, and let's say if they're, for example, you could take a random variable in -1 and 1. So for example, this could be, let's say AIJs could be Bernoulli, let's say -1, or Rademacher, let's say. It is symmetric Bernoulli, -1 and 1 with equal probability. Okay, so equivalent is saying that like +1 -1 with probability 1/2. So this is an example where the mean is 0 and they're sub-Gaussian, and sub-Gaussian norm is constant. And so in this result is saying that you basically flip each entry with equal probability to be +1 or -1, then their operator norm would be of the order root m plus root n, which is much smaller than the maximum that can be, which is root m times n. Okay, and this is sort of general idea in probability and statistics that sort of sums of independent centered random variables are not growing as fast as deterministic sums. So if you have, for example, some independent zero mean random variables whose variance is bounded, then the sum grows like root n, not like n. And that's sort of the variance. So you can argue by the variance bound or the CLT or something like that. Okay, so any question about this statement? It's just a recap of the last time. No, okay, so sorry, let me see if I can connect back to, give me a second. So, okay, sorry. I need to see the chat window. Sorry, okay. So we basically proved this result using the so-called discretization argument. Briefly going through it again. So you can argue that the operator norm is bounded by, the operator norm can be written in this variational form, supremum of ax inner product with y, where x and y are in the this is not quite correct, because so I'm assuming that this is m by n, so we should have x in r n, I guess, and y in rn. Sorry, the spheres. So the sphere of radius 1 in Rn and the sphere of radius 1 in Rn. So this is what we need. And then you can put an epsilon net on the set, or find an epsilon net for the set. So n is an epsilon net for the sphere in Rn, or the ball in Rn, and m is an epsilon net for the corresponding sphere or ball in Rm. And so if I replace the supremum over this basically uncountable set, which is the Cartesian product of basically replace sup over Sn minus 1 cross Sn minus 1 with sup over n cross m, which is the finite set. I pay a price which is at most this much. And if I take, for example, epsilon to be 1/4, then this price is a factor of 2, which is, for us, is very mild price, because we don't care much about constants. So, and with epsilon or 1/4, we have seen that, for example, you can cover these balls or spheres with this many points. So if epsilon is 1/4, this gives me at most I need at most 9 to the n or 9 to the m for covering these sets, the spheres. And so the idea is that we, in order to prove, you come up with a tail bound for this quantity for a fixed x and y. So this quantity, we saw it's a sub-Gaussian variable, and so we get this tail bound for it, this guy, and then you would sort of bump this to a uniform bound by using the union bound. So if I take the maximum over this Cartesian product, the maximum is going to be bigger than or equal to that if and only if there exists one of the elements of this set that is above that threshold, and that probability is bounded by the sum of the probabilities of those events, which is bounded by basically cardinality of the set times this tail bound that we have here. Okay, so that's the main. So this equation, this is the main sort of, or this inequality is the main sort of result that we have. Then the final step is to choose u such that this side is basically not growing with n or m. And so we saw that this choice that we made here would cancel this exponential term, and so you get e to the negative t squared, and then with this, so the u appears here, and so the u, if you take the root of this, it would be of the same order. So if you go through the details, the rest follows. Okay. So the key is that the main idea here is the union bound over this, which pays this exponential, for which we pay this exponential price, and then there's this nice exponential here, which comes from the sub-Gaussian tail bound, and we can use that to kill that exponential term. Okay, that's the basic idea. Sounds good. Any questions about the details of this argument? Okay, seems like people are okay. So let me make a comment here that for Gaussian variables, or for Gaussian matrices, assume that you have standard Gaussian elements for each entry of the matrix, there are sharper bounds. So you can get a much sharper bound. So you can basically get this result, that this bound with constants being like 1 here, root n plus t, holds with probability 1 minus this much. Okay, so they're explicit constants. And this result, for example, follows if you apply the concentration on Lipschitz functions of Gaussian vector. So this operator norm, so A maps to operator norm of this is a Lipschitz function of A viewed as a vector. Okay, so why is that? Why is this a Lipschitz function? So think of A as a vector based stacking, let's say columns, and the space under which I'm taking the Lipschitz constant is like the Euclidean space. So you're working with the L2 norm on the Euclidean space. So why this function is a Lipschitz function? Anyone knows? A maps to operator of A.
It is because the operator norm is the largest eigenvalue, and so you can probably
yeah, it would be largest singular value.
Yes. And
okay.
No, not that.
This is bounded by the sum of singular values squared. So what is this sum? If I sum singular values squared and then take the square root.
And this is the Frobenius norm.
Yes, so this would be the Frobenius norm. So this little argument shows that the operator is bounded by the Frobenius norm. Okay.
Mm-hmm.
Now what? This is the L2 norm
of the
vector. Yes, x minus y.
Okay, got it.
Yes, so you can see if you define this, and then this other side is further. I can write something like this: f of a, or f of. So I'm going to do this. We've done this before, I believe, but I guess people have forgotten it. So f of x minus f of y, where f of x is just operator norm of x. So y expectation plus t is bounded like this. Okay, so I have this tail bound, which we get from concentration Lipschitz function. This is a 1 Lipschitz. So you can see Lipschitz with constant 1. What remains to show is this expectation is bounded by root n plus root n. Okay, so if I can show that, then I have this result. And this is not easy to show in general. And there are some techniques, which is so you could obtain it by using the Asclepian or Sudakov-Fernie. These are kind of Gaussian comparison inequalities. And we'll skip that part of the book in chapter 5. We'll see if you get time. Usually we don't get time to go through this. If you're interested, you can take that you can take a look at that part, or you can pick up that part as your project. This is a very different approach than an epsilon net argument. It's the alternative approach of bounding things in terms of supremum Gaussian process or supremum processes. So you can write, you can think of the, basically, see if I can write this here. So you can think of the expectation, or let's say you can write the, sorry, this did not work. Should I do it here? I'm gonna add a page here, see. Okay, no, I want it here. Okay, so I can write a operator norm as C as supremum of, I read it like this, A U V, right, U in S, this is M by N, let's say, it's N minus 1 V in. So you can write it as supremum of something like that, A times, sorry, what happened here? Let me try this. So this is basically A U transpose V, or U transpose A transpose V, which I can write as also as, let's say, trace of A transpose V U transpose. Okay, which can be written as the inner product in the matrix domain, let's say, of V U transpose. This is a inner product, if you remember. So A B, I'm gonna write it like this. And write this trace of A transpose B. This is going to be just the usual inner product, viewing this as vectors. So this I can write as supremum, or the same set of A V U transpose. And this is a linear Gaussian process. So this guy, so this guy, VU transpose maps to A VU transpose. This is a Gaussian, linear Gaussian process. Linear Gaussian process indexed by these indices where U and V. So V is in Sm minus 1, U is in Sn minus 1, and then you can compare. So what you're doing is you're looking at the supremum of this random process, and you can compare this suprema to suprema of simpler processes. So I'm just going to mention the approach, but don't go into detail. So we can compare the suprema. This process to that of a simpler Gaussian process. And from that, you get this result. If we have time, we can go through it, but these are called Gaussian comparison inequalities. So you compare suprema to Gaussian processes. Hopefully one of them is easier to compute, and then you get that result. Okay, so if you're interested, check chapter 5 of HDS. Okay, I'm just telling you that this exists, and in case you want it, it's very useful to remember this result. Hopefully the constants are correct, but if you want to remember one result, this is a good result to remember from this chapter. Okay, so questions? Okay, so let's move on. What I want to do now is talk about a more interesting case, which is the case of covariance matrices, concentration covariance matrices, and or basically the sample covariance matrix. And the sample covariance matrix is not, the entries are not independent. but we'll see. And then the IID assumption also is not that interesting when we deal with not IID, but all the coordinates being independent is not interesting because we care about covariances, so we want to estimate the covariances. So before doing that, before studying sample covariance matrices, let's extend the definition of subgaussianity to vectors. Okay, and this is, I believe, this section in the high dimensional probability book. So we say a vector, a random vector x, has a subgaussian distribution if you take look at these inner products. So inner product of x with any vector u in S d minus 1 on the sphere, basically. So you take the inner product of x with any vector in the sphere, and that is subgaussian. If that's the case, then we call the vector x subgaussian vector. And this definition is modeled after multivariate Gaussian distribution. Okay, so if we change sub-Gaussian to Gaussian, we get the definition of a multivariate Gaussian random vector. So one way to define a multivariate Gaussian distribution, multivariate Gaussian random vector is exactly like this. So you'd say these, you can say one-dimensional projections if you want. One-dimensional projections of the vector are all Gaussians. Then that vector is said to be Gaussian. That's a general way of defining, let's say, multivariate distributions from univariate distributions. So, have you both seen this before for Gaussian? That's how you define. Anyone has seen this before for the multivariate Gaussian?
Yes.
Yes, okay. Good, okay. So if you haven't seen, this is a good way of defining it in general. So let's say if you have a, like an abstract space, you want to define a Gaussian distribution on that abstract space, and you know how to define functionals. So functions that map elements in that space to reals. Then you can require that the Gaussian distribution in that space be any distribution whose when you apply these functionals to the element, those turn out to be like univariate Gaussian random variables. In any case, so this is the definition of a sub-Gaussian random vector. And then you can define a sub-Gaussian norm for the random vector by taking the supremum of the sub-Gaussian norm of these, I would say, one-dimensional projections. Okay, so the largest or the maximum of these sub-Gaussian norms is defined to be the sub-Gaussian norm of the random vector. Okay, and then there are a couple of observations here. So any vector with independent sub-Gaussian coordinates is going to be a sub-Gaussian vector. And this is the lemma in HTTP, and you can also prove it for yourself. And the sub-Gaussian norm is going to be a numerical constant times the maximum sub-Gaussian norm of the coordinate. This is not difficult to show. But there are other examples where the coordinates are not necessarily independent. For example, suppose you have a random vector which is uniformly distributed on the scaled unit sphere in RD. So this is, say, sphere. This is going to be root ds d minus 1. So if I rescale the sphere right like this, and if my random variable is distributed, let's say uniformly on the sphere, then you can show that this is a sub-Gaussian random vector whose sub-Gaussian norm is bounded by constant.
Why do you scale it with square root of D?
That's a good question. So this is, so let's say it's going to make it similar to, that's the right scale for this to have some Gaussian norm constant. The reason to see it is that because things that look like this are basically, it's very similar to something that has like a Gaussian with covariance identity. Okay, so the norm of X would be
I see.
very close to, in this case, or let's say D if you want.
But
in this case, the norm of X would be very close to root D. So this is almost uniformly distributed on that sphere. They're very close. And it's easier to see that for this guy. For example, from this, you see that the sub-Gaussian norm is constant. Okay.
yeah,
and
but you,
yeah.
if you do not scale with square root of D, you will still get that result, but not with the constant C, but with something else, right? Or not?
Yeah, so that would be like dependent on dimension. So let's say if I define Y to be X over root D, right? Then this would be on, so if
I see, got it.
Yeah, if X is right uniform root D S D minus 1, then this guy would be uniform on the sphere. And so the sub-Gaussian norm of this guy would be 1 over root D times the sub-Gaussian norm of X.
Yeah.
So this goes to 0.
Okay.
Which is fine, but generally we care about like things that have constant, but they're related. So okay, and then no problem. And we can also extend it to this general Gaussian random vector, and you can show that then this is a sub-Gaussian random vector, and the sub-Gaussian norm is bounded by constant times the operator norm of the square root of the covariance matrix. Or if you want, you can write the operator norm of this square root, put a square root there. These are equivalent. The way to show it is you write X as root sigma times Z, where Z is standard Gaussian vector, and then you apply the next lemma. What is the next lemma? The next lemma says that if you have a sub-Gaussian random vector, and then you have a deterministic matrix A, then A times X is sub-Gaussian random vector with sub-Gaussian norm controlled by the operator norm of A times the sub-Gaussian norm of the original vector. Okay, and if you plug in this result, then you get this value. Okay, questions? And this result is quite simple. I could have assigned this as a homework problem, but maybe too simple for a homework problem. So the way to show it is just by definition. So you'd go, I have to look at these one-dimensional projections of AX, and if I define this is going to be equal to by like the adjoint property, or just do it as expanded and in terms of transpose, this is going to be like that. I call this V, right? So this is going to be this. By definition, this is going to be bounded by this. If you want, there's a little step here, so that you multiply and divide by this, then this is a unit norm vector, and so the sub-Gaussian norm of this is bounded by definition. The definition is that this is bounding the maximum sub-Gaussian norm of these one-dimensional projections. So this is going to be bounded by this, and so this follows. So you get that, and this thing is just bounded further by the norm, operator norm A transpose times U2. And the operator norm of A transpose is equal to operator norm of A. as an exercise, you can try to show this. And so this is the result false. It's really not that difficult to show. Okay, sounds good.
Yes.
Okay, so you can see there are multiple examples, in particular this Gaussian, the general covariance matrix, the entries are not independent at all. It could be very dependent. But you still have, you have that this is a sub-Gaussian random vector, and you usually care about the case where the sub-Gaussian norm of the vector doesn't scale with, and it doesn't scale, for example, or with dimension, it doesn't scale if the operator norm of sigma is controlled, right? So you could have that the dimension grows, but the covariance matrix operator norm doesn't grow that fast. Then you have quite good concentration for, or at least this is going to be a sub-Gaussian random vector. And we can write like interesting concentration inequalities for these things. Okay, clear, people? Okay, so if so, let's now move on. So now I'm going to talk about concentration of the sample covariance matrix. And this is an interesting result of, and we can use the techniques that we have learned so far, basically, to drive, I would say, an interesting result, which is not trivial. So the idea is that I have let's say, basically x1, x2, xn. These are independent, not necessarily identically distributed, and I also know that the expectation of each, like x, the second moment, basically, this is sigma for all I. I'm not assuming that there's zero mean, and so the sigma is not necessarily a covariance matrix, but let's say if there's zero mean, that you can interpret the sigma as the covariance matrix. So they're independent, not necessarily identically distributed, but the second moment matrix is the same. And I also assume that I have a bound sigma on a sub-Gaussian norm of these vectors. So these are sub-Gaussian vectors. So assume that these are sub-Gaussian vectors, and so they have a norm as a sub-Gaussian vector, and the norm is bounded by, so the sub-Gaussian norm of this is bounded by a sigma for all I. Okay, so the setup is something like, so I have a matrix, data matrix X. So this side is D, and this side is N. And each row here, the ith row basically, is Xi transpose. The other way around, sorry.
You mean N by D?
Yes. So that's the other way around. Thank you. Okay, so that's one like row, and so if this is my data matrix, so that would be X, then I can form the sample. I'm calling it a sample covariance. It may not be the sample covariance, but in the case where there's zero mean, that's correct. So that's the that's my sample covariance matrix, which can also be written as 1 over n x transpose x. Okay. So by the law of large number, this guy is sigma. You would write it as sigma hat n, let's say. This converges in probability to expectation of x1 transpose, which is just sigma. Okay. Right. So we can study whether.
But you didn't assume that all the xi's are from the same distribution, right?
Right. So is the weak law of large numbers still correct there? That's a good point.
How can you conclude that sigma hat, and because what is sigma?
So I'm assuming that sigma is the same. So they don't have the same distribution, but the second moment is the same.
I
Right?
see. Okay.
That's the minimal assumption.
Okay.
And you can most likely show that if these are, let's say, the second moments are bound, or the I don't think actually you need anything else. You probably can show that with this assumption, that the fact that the sigma is finite and the same for everyone, basically, then this converges. You probably try to show this. It's not the classical these large numbers that assumes that entries are identically distributed. But it's very plausible that this is easy to show. Okay, so you can show. In fact, what we show here is actually we're going to show that under sub-Gaussianity we prove this. We drive a bound. So what we want is we hope that this is true. The yes, the convergence probability, you need some sort of a norm, so you can prove it in like various norms, or you can prove it coordinate-wise. General idea is that if you want finite sample bounds, you have to pick a norm, and depending on the norm that you pick, the scale of convergence would, or the rate of convergence would be different if it converges at all. And so the tricky part is picking the right norm, and so we care about, we want to control the operator norm. Okay, this is interesting because this is going to be related to the eigenvalues and eigenvectors. If you control the operator norm, you have a control of the deviations of the eigenvalues and eigenvectors. Okay. Okay, so is a problem clear? So we hope that this is, we hope that we hope to show that this is small. This deviation small. I shouldn't say that because well, we're going to bound this, whether it's small or not. There's going to be a bound that holds. You hope that it's small, but may or may not be small. Okay, so here's the result. So the result is saying that, write it here. Theorem says that, let's say sigma hat n minus sigma, the operator norm up to constants bounded by that sigma, little sigma, which is this bound on the sub-Gaussian entries, times basically root d over n plus d over n, and then plus a little delta here. And this holds with probability bigger than 1 minus some constants e to the negative another constant and minimum of delta and delta squared. Okay, so that's the type of result that we have. In general, this sigma, so sigma squared, so this is, let's call this supremum of the sub-Gaussian norm of these entries. This is going to be bounded by the operator norm of sigma. I'll talk about this. But if that's the case, then this bound, I can just replace this guy here. I can replace this with the operator norm. Sorry, this would be operator norm squared. Is that? Yeah, this should be operator norm squared, I believe. So I should be able to replace this with operator norm. So if you ignore delta, or you can set delta, this is roughly saying that sigma hat n minus sigma operator norm is bounded by the operator norm of the sigma times root d over n plus d over n. Okay, so for example, if if n is bigger than or equal to d, what would happen here? So if n is bigger than or equal to d, which one is dominating? Is root d over n bigger or d over n?
Root d
bigger?
over.
Yeah, so we get root d over n up to constants. And so for example, if I want to, so I'm assuming this under this assumption. So if you want to have sigma hat n minus sigma operator norm is less than or equal to, let's say, epsilon times sigma operator norm, then it is enough to have basically root d over n less than or equal to epsilon or up to constants, or n bigger than or equal to 1 over epsilon times d. Okay. So this is saying that you need the sample size that you need is, let's say if epsilon is fixed, is of the order of d. And this is quite interesting because the matrix has, in general, let's say d squared entries. Whereas the sample size that you want for the operator norm to be controlling operator norm is of the order d, not d squared. Okay, which may not be that obvious at first. So you don't need quadratic sample size quadratic in dimension, but linear in dimension. Okay, any question about this statement or the conclusion that we have here? Questions about this?
Will you also do the sub-exponential thing? For
What
this,
do you mean?
I mean, this one you analyze for the sub-Gaussian, right? Will you also
Yes.
do this for sub-exponential?
I am not going to do it for the sub-exponential one, but you're welcome to try to show it.
And what
Yeah.
Statement is that? Just want to know.
Whether something like that just holds true.
Yeah.
I'm not sure, to be honest. We're going to go through the proof, and you'll see there are certain areas that we use sub-Gaussianity. Whether it's a good question. No one has asked in this course before, but you can try to think about this and see if the argument goes through. The argument is very general at some point, but you invoke the sub-Gaussianity, and you can try to see if you can replace that with sub-exponential concentration, and if things would work out. It's a good question.
I have maybe
yes.
like a comment. It seems like this is using the fact that when you like multiply two sub-Gaussians together, they're sub-exponential, because the bound itself looks sort of like a sub-exponential bound. And
that's correct.
Here we have, like, for the covariance, we're having like a bunch of it's like sums of like products of a pair of Gaussians.
Yeah,
so I'm not sure how to do it with sub-exponentials, because when you square sub-exponentials, it gets worse.
That's the right answer. So did you get the like?
No.
No. Okay, so maybe you can say that again, Daniel.
So here we have a bunch of like the covariance matrix seems to have something like it's analyzing like products of the Gaussian or sub-Gaussian random variables, which the products of a pair of them are sub-exponential. if you look at the actual bound, it has the same form of like the minimum of delta and delta squared. And so that looks like the similar sort of sub-exponential bound we were seeing in the concentration and inequalities part. But so it seems like we don't have something like this for squares of sub-exponential, because then the tail behavior is maybe not as nice. So I'm not sure if it would work.
Yeah, so that's exactly, so you can see it, and we'll see it in the proof. And I didn't notice it, but that's exactly what happens. So if you do look at the entries of this, so if you think of the, see, for example, look at the ijth entry. So this one, or let's say jk entry. Okay, this is the 1 over n sum I from 1 to n xi transpose jk. So this is 1 over n sum I from 1 to n xi j x I k. Okay, so this is a sum of a bunch of products of some Gaussian variables. Okay, so products of sub-Gaussian variables in general become sub-exponential, like the upgrade in the hierarchy. So you like your tail becomes heavier. So if these were sub-exponential, when you multiply them, you could go outside the sub-exponential family. Right?
Yes.
So you need.
Yes,
You
I mean,
need like.
yeah, I understand that, but what I was asking that, like, is there any other bound which we know that holds for sub-exponential?
Okay, so you're saying whether there is so that I don't know. So you can try to search there. You can still like the issue is that your at that point there's no like unifying class that contains these. So it could be like for certain classes of sub-exponential variables, these products behave well, and then you have nice results. For certain other sub-exponential variables, this might not be nice. So the question is whether there's a general useful result for that case that may or may not be, right?
I remember seeing it somewhere. Yeah, but I don't.
Okay, you can if
Okay.
you can find it, I'd be interested to see. You can post it on campus wire.
Okay.
Yeah, the question is whether you could maybe come. So there, for example, you might end up like bounding using not Chernoff bound. You can use, for example, the polynomial Chebyshev type bounds and try to optimize that. The question is that whether there's a general bound that is useful for all sub-exponential cases, or then you might have some sort of divide the cases into further subclasses for the bounds to be more useful. Okay. Good. A good question. If you can find something that would be interesting thing to see. You can see discussion quickly becomes like these questions are at the border of research, I would say, at this point. So if you want to manipulate things a little bit, not everything is known at this point in great detail.
Probably, I have seen the result when your columns are IID, and the parameters for the sub-exponential, you have two things, right? And nu and
Yes.
those are like the ratio that is omega of 1. For that, I think I have seen this somewhere.
If you can find it, that would be interesting. But the question, the thing is that even if that's the case, then still the product, I'm not sure. You could still get something which is very ill-behaved, I'd say, even if like those parameters are controlled. I'm not sure. Maybe you can control it. Maybe.
I see. I'll.
But
See.
right, but this, yeah.
And you are saying that HDP book does not have that, or?
I doubt it. You can check. I don't remember seeing it there.
Okay.
Yeah.
I see. Okay, thank
you. But it's a very good question. No problem. Yeah. And it was a very good answer. So other questions? Okay, so how do we prove this? Let's see how much time we have. So how do we prove this? how to prove this. Anyone has any general plan of how to prove this? How to approach, let's say, proving this? So I'm going to help you out by, so we're going to use the variational characterization. So I have, let me cheat a little bit. I guess I use U there. So I'm going to write this as the supremum U in, so this is going to be a d-dimensional matrix. So U in SD minus 1, absolute value of U, sigma hat minus sigma U. This is one of the variational characterizations of the operator norm that you can do for, you can write for symmetric matrices. Okay, so this is true. In other words, this is just U transpose sigma hat minus sigma U. Okay, so now what is the next step? Actually, the next step is to simplify this a little bit further. So I'm going to write a page here. Oh, not work. Why this happens? Sorry. Okay, so U transpose sigma hat n minus sigma U is just U transpose sigma hat n U minus U transpose sigma U. Okay, and this one is 1 over n summation I from 1 to n U transpose xi and then xi transpose U minus U transpose sigma. So is there any simplification they can make here? Any comments? Okay, I'm going to continue myself. So this is going to be 1 over n summation I from 1 to n. So these two terms are the same. They're transpose of each other and they're scalar. So I can write it as, for example, U transpose xi squared. Okay. And this guy is basically the expectation of each one of them. So this is the expectation of U transpose xi transpose U. And so I can just write it as negative exponential U transpose xi squared. Okay. So this is the summation of centered variables, independent. They're independent because the rows are independent. So the average of independent, centered, right? Okay, does this make sense?
Yes.
Yes, okay. So now what? What can we do now? So what is this random variable? What type of random variable this is? I'm going to continue because was already pointed out. So this guy is going to be sub-exponential, right? Because if I take this, if you remember, this is the sub-Gaussian norm of this guy squared. right? And the sub-Gaussian norm is bounded, so this sub-exponential norm is going to be bounded. So U transpose xi are sub-exponential. So what is the sub-Gaussian norm?
I mean, U transpose xi squares are sub-exponential, right? Not U transpose xi or sub-exponential.
Yes, what I'm saying is that these are sub-exponential. All right, right.
So you wrote on the right side.
Yes, right. This is also true, but they're better than sub-exponential. Okay, so these are sub-exponential. Yes.
Okay.
So now U is in the sphere. So what can I do about this expression? Can I relate it to the sub-Gaussian norm of the vector xi? Can I say something like this? I can say it, and in fact, I can drop this because that's unit norm. So I get this. Why? If you go back to the definition, that's what it is. So the sub-Gaussian norms of these projections, univariate projections, are bounded by the sub-Gaussian norm of the vector. Okay, I have one of these here, and so that's what I get, and this is by assumption bounded by sigma squared. That's what I define as sigma squared. Okay, so now how about this guy? U transpose xi transpose minus expectation of U transpose xi squared. What can we do about this? Do you remember a property or like a little lemma that helps with this situation here?
Yeah, this is this is up to constant, same as the psi1 norm of U transpose xi square.
Right. So this is the centering idea. Centering lemma, which is bounded by sigma squared. Right. So you can see the sub-Gaussian norm, like the sub-exponential norm, this is bounded by the sub-Gaussian norm squared of the vectors. Okay. So now, what can we do here now? We can use the Bernstein inequality, right? Do you remember? So this is a sum of centered sub-exponential random variables. So we can say that the probability. So if I call this guy, let's say Sn. Let's call this Yn. So the probability that Yn is bigger than or equal to delta is less than or equal to e to the negative minus, do you remember the Bernstein? Let's see if we have the Bernstein here somewhere. Okay, so let's go back to the Bernstein. Okay, I'm going to use this. So the average is bounded by. So this is so we have control. So we have k here. K is going to be sigma squared for us. So if I apply that, I get like probability that Yn bigger than or equal to t is less than or equal to 2x negative c n min t squared over sigma 4, sigma to the 4, and t over sigma to the 2. Okay, that's what I would get. see if I can cut this out. Cut. Go back here. Add this one. Paste. Okay, so that's what we get here. Okay. So that's what we got. Right. I can do a little bit of simplification. So first, I'm going to write this as, this is what we have shown. This yn is basically, remember, yn is just this. So what I have shown is the absolute value of, let's say, u transpose sigma hat n minus sigma u, or if you want, write it like this, u. Yeah, just that. That's good enough. Bigger than, I'm going to replace t with sigma squared t. So if I do that, I get sigma squared t here, less than or equal to twice x negative c dot n dot min t squared and t. Okay, that simplifies the expression a little bit. So this holds for any t greater than or equal to 0. So what is the next step? So I have this for any fixed u. So this holds.
Union bound over the net.
Yes, so then we're gonna take the union bound over the net. Next step, union bound over the net, epsilon net. I would say, for example, so if you go back up, you can see no, I don't have it here. So a similar trick holds for, I forgot it. It's probably with 2. So you could say that let's say 1/4. We're going to use 1/4. It's similar to the 1/4 net of s and d minus 1. So this, call this, for example, n with cardinality of n being less than 9d. Okay. So you get that the probability that supremum of u in n is bigger than sigma squared t is less than or equal to, let's say, 9 to the d, and then 2x negative c n min t squared and t. Right. Okay. At this point, we're almost done, and this is further sort of, if I do it like 2 here, put a 2 there, I believe this is going to be an upper bound. So yeah, what we have here is operator norm. This would be sigma u. The operator norm is bounded by supremum, twice the supremum. Right, so I can replace this side with this guy and still get the same bound. So what I have to do now is to just control this probability. Okay, and this is a little bit tricky because we just have this minimum there, which is a little bit problematic. But so far, is it good so far? Yes. People are happy with this. So it's not that different. So the techniques are very similar. So you come up with a variational characterization like this. You use discretization to replace this soup with soup over this. We didn't discuss this. We did it for non-symmetric matrices, but for symmetric matrices it's similar. So you can go through the same argument, I believe. You get a factor of 1 over 1 minus 2 epsilon. So you pay that price. So you need a 1/4 net, similar to the idea. So just verify this for yourself. So check that this holds if n is a 1 over 4 net. So we did the discretization for any fixed u. We had like a concentration bound using the sub-Gaussian, sub-Gaussian and sub-exponential concentration. So Bernstein basically. Bernstein for sub-exponential variables. And then we used union bound to finish the bound. And now I need to choose t so that I can kill this thing that's growing with d. Okay, so here I'm going to use a trick, which is not necessarily a trick, but let's go down here. So there is this simple observation that you can make. So if you look at a function like this, maximum of delta and delta squared, you can argue for yourself that the inverse of this function is going to be the root of the minimum of t and t squared. Okay, so these two functions are the inverse of each other. So you can do it by plotting and reflecting with respect to that 45-degree, or however you want. Just do it for yourself. It's a little bit more general. So if things are monotone, the maximum of fi inverse is the minimum of the inverse of fi. So if this is true, then this means that if I set this side equal to like a square, so this is saying that if t is equal to the maximum of delta and delta squared, then the minimum of t squared and t is equal to delta squared. Okay, this is another way of stating this. So these are inverses of each other. So why this is interesting, because I can here simplify. I can move this to the take this to be delta squared. Okay, so take this to be delta squared. So set delta squared to the minimum of t squared and t. From this, we conclude that t should be the maximum of delta and delta squared. Okay, that's this little trick here. Okay, so I can conclude that I can write that the probability that I'm going to just replace this here, sigma hat n minus sigma up is bigger than or equal to 2 sigma squared times max delta and delta squared is less than or equal to 9d 2x negative c delta squared. Okay, that's the little trick. So
you also have n, a factor of n.
Yes,
in the exponent.
Good, right. C and delta squared. Now we're back in business. I can take. So what I would like to do is, so this is basically equal to 2x d log 9 minus cn delta squared. Okay, so take, for example, so what I would like is basically C and delta squared be d, let's say, log 9 plus, I don't know, plus, would this work? Something like this. Right? So if I have this, then this is going to be bounded by 2 x negative u squared. Okay, so we have here. There's an n there. So what I would like to have is, yeah, I would like to have n u squared. Right? That would be a little bit better. And at this point, it's a little bit. Okay, so if I take it to be that, then I'll kill this term, and I get this extra factor here. Okay, so with that choice, for some u, I get this, and then I also have that delta would be d, let's say log 9 divided by c, let's say log 9 divided by c d over n plus 1 over c u squared, root of this, right? And it's going to be bounded by bounded by what? I'm going to ignore the constants, up to constants bounded by root d over n plus u. Okay.
You also probably want to take u to be order of d over u squared to be order of d over n in order for that c and delta squared to be minimum.
What was that?
I mean, your c and delta square is d log 9 plus n u square, where u is up to you, right? I mean, you can choose the value of u, right?
No, I wanna keep u in the bound. So I want.
Oh, okay.
I want to let u be in the bound. Okay.
I see. I see.
Right, but is this correct? So far, I see is correct, right?
Yes. Yes.
Right. Okay. If I have this, then what I would get is that. So this side of the bound is fine. I now have to worry about this. I get maximum of delta, and delta squared is maximum of basically root d over n plus u, right? And then d over n plus up to constants, right? U squared. There's a factor of 2. If I square it, I get this twice that. So here I'm using, let's say, a plus b squared is bounded by 2a squared plus b squared. I'm absorbing 2 there. So that's case. And then I believe I can do, this is going to be bounded by, let's say, up to constants bounded by root d over n plus u plus d over n plus u squared. And then up to constants, I can do like root d over n plus d over n. And I can, right, plus maximum of u squared. So sums and maximums are within factor of 2 of each other. So I can do this. So what I end up having here is that the probability that what I've shown is, so if you go back up and replace this, you get that the probability that sigma hat n is less than or equal to, sorry, bigger than or equal to 2 sigma squared times, there is a constant here. So whatever constant, C1, let's say, root d over n plus d over n plus max u and u squared is, this thing is bounded by 2e to the negative nu squared. Okay, that's what we've shown. And this is as good as the original, the bound in the statement. If you want to get it in that form, you can also call this another thing. So call this, I'm going to call this, for example, epsilon, right? So if you call epsilon, then you can again revert back. So if epsilon is maximum of u and u squared, then from this calculation you see, then epsilon squared is going to be minimum of u and u squared. Okay, so no, sorry, u would be not this. Then u squared would be minimum of epsilon and epsilon squared. Okay, this is this business. So if this is epsilon, this is u, then this is going to be u, this is going to be epsilon. Sorry, this is going to be u, this is going to be epsilon. Yeah, in any case, so that's the trick. So you can translate from this side to the other side. So if I do that, then I get the probability that sigma hat n minus sigma operator norm is less than or equal to 2c1 sigma squared root d over n plus d over n plus epsilon bounded by 2x negative n minimum of epsilon and epsilon squared. Right, this is the bound that we want. So if you go back here, that's exactly what we hope to show. Okay, we're a little bit out of time, sorry, but that's basically what we have done. So at this point, after this point, there's a little bit of tricks of translating back and forth, but this is very helpful if you're working with sub-exponential variables, if you understand this inversion. You can move from one side, you can move things from the upper bound to the probability side and back. Okay.
Yeah.
Questions, comments? Okay, so thanks for listening, and I'm going to hopefully post the next homework soon. So be on the lookout on Campus Wire. I'm going to post an announcement. And okay, so we're done with this slides, and I'm going to come back next time and talk about structured covariance estimation. So we talked about this, but this bound is not quite good because it's good, but in high dimensions, this is not useful because p is much larger than n. So we're going to come back and talk about things like sparsity and how to deal with that for covariance matrices. Okay, thank you, and see you next time. Goodbye.